Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथरे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि एबे मु प्लस 3 सीबीसीएस ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि तमे ताकू पढे मध्ये परिबो एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रो तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई की रखिथिबी तमे सर्च करि परिबो ओके थैंक यू हेलो स्टूडेंट्स आज रो टॉपिक रे हमें CNT बेस्ड ट्रांजिस्टर्स ए विषय रे पढिबा so first of all CNT means carbon nanotubes. So let us first briefly know about the carbon nanotubes. Okay, so these are cylinder shaped macromolecules which are made up of carbon atoms, and these CNTs are actually allotropes of carbon with very unusual properties, and it can be used in case of your nanotechnology, electronics, optics, and other fields of material science and technology. Okay, the carbon nanotubes are actually similar in structure to the fullerences, except that the fullerences are spherical, whereas the CNTs, that is the carbon nanotubes, are cylindrical in shape. Okay, and these CNTs are actually discovered by a Japanese scientist S. Ijima in the year 1991. Okay, so the carbon nanotube is like that of a sheet of graphite, that is graphene, which is rolled into a tube with bonds at the end of the sheet, which are forming the bonds that close the tube. Okay, so the graphene sheet is shown in this figure. You can see it is somewhat like the nest of a honeybee, right? So the walls of the CNTs are made up of hexagonal lattice of atoms. Okay, you can see this is a hexagonal shape. Okay, 1 2 3 4 5 and 6. Okay, so it is made up of a hexagonal lattice of atoms and are kept at their ends by one half of a fullerene like molecule. Okay, now these carbon nanotubes actually are very unique because the bonding between the atoms is very strong, and the tubes can have extremely large aspect ratios, which is the ratio between the length to its diameter. Okay, so these CNT can have diameters of few nanometers, and length will be of the order of hundreds of microns, that is 10 to the power minus 6 meter. Okay, carbon nanotubes can have many structures differing in length, thickness, and number of layers. Okay, and their characteristics depend upon how the graphene sheet has been rolled to form the carbon nanotube. Okay, so here the graphite layer that actually makes up the nanotube will look like rolled up chicken wire with a continuous unbroken hexagonal mesh, and the carbon molecules at the apex or vertices of the hexagons. Okay, so here the chemical bonding of the nanotube is actually composed of entirely sp2 bonds, that is sp2 hybridization bonds. Okay, which provide nanotubes with their exceptional strength. Okay, so basically the carbon nanotubes are the strongest, lightest, and most conductive material known. Okay, this is conductive to heat and electricity. Okay, now let us see what are the various types of carbon nanotubes. Basically there are, although many different types of carbon nanotubes, but generally if we categorize, then it will be of two types: either single walled, that is SWT, means single wall nanotube, or multi-walled, that is MWNT, multi-walled nanotube. Okay, so multi-walled carbon nanotube were discovered in the year 1991, whereas single walled carbon nanotube was discovered later in the year 1993. Okay, single walled carbon nanotube is just like a regular straw. Okay, this one, okay, and it is made up of one atom thick single layer or wall of graphite called your graphene, okay, and most single walled nanotube have a diameter close to 1 nanometer, but it can be as long as 100 micrometer, that is 100 micron, okay. Now the second figure is that of your multi-walled carbon nanotube or MWNT, and here it is having a diameter of 2 to 100 nanometer, okay. So this multi-walled carbon nanotube, actually these are a collection of nested tubes. You can see this is one tube, this is another tube, this is another tube, so these are nested, okay, and continuously increasing in diameter, okay. This is having a diameter which is comparatively less than this one, then the greater diameter is having this one, okay. So the diameter is continuously increasing. Thus the multi-walled nanotubes are actually the nanotubes within nanotubes, okay, nanotubes within nanotubes, right. Now here the diameters of these multi-walled nanotubes can be between 2 to 100 nanometer, and their length can be up to 20 centimeter, okay, 20 centimeter in length, and it can range from one outer and one inner tube, that is a double walled nanotube, to as many as 100 tubes or walls or more, okay. So this is suppose one wall, two wall, three walls, so up to 100 walls it can vary or even more, okay. And each tube is held at a certain distance from either of its neighboring tubes by interatomic forces, and the forces between the carbon atoms of different layers of this MWNT are weak van der Waals forces, okay. So this is all about the basic knowledge of carbon nanotubes, that is CNT, okay. Now let us come to our main topic, which is the CNT based transistors. Now you see from this name, the CNT based transistor means obviously these are the transistor in which the carbon nanotubes are used, okay. And you have already read about the field effect transistor in electronics, that is FET. So when carbon nanotubes are used, then it will be called the carbon nanotube field effect transistor, that is in short CNT FET, and these are the CNT based transistor, and it is very much similar to the MOSFET, that is metal oxide semiconductor field effect transistor, okay. So it is similar to the MOSFET in today's technology. Now these CNT FETs actually require three terminals, namely as in case of your FET, so here source, drain and gate, okay. So here the CNT FET carbon nanotubes are used as the channel material, but in case of your MOSFET, actually it is heavily doped with silicon and it is used as channel material, okay. So CNT FETs are of two types, namely N channel CNT FET and P channel CNT FET, okay. So this is the figure of the CNT FET, as you can see. So here the diagram from this, you see this is the source, this is drain and this is gate, and the nanotube is this one, okay, this black one. So the nanotube is actually passing through this, okay. Now this is a silicon dioxide layer, now this is a gate oxide, and at the bottom we have a silicon wafer, okay. So here the gate is placed on the top of the carbon nanotube, and the gate is separated from the nanotube by an insulator, such as this gate oxide, which is an insulator, and it is much thinner, having thickness about 15 nanometer, right. And the nanotube is sealed so that the air will not cause the CNT FET to act as a P channel CNT FET, okay. Now let us come to the various types of these CNT FET. The first one, which is the P channel CNT FET, okay. It conducts the holes, okay. As you know, P means here the holes will be the majority charge carrier, so it conducts the holes when a negative voltage is applied on the gate, and it does not conduct the electrons even at high positive gate voltage. Okay, so for this, following procedure is used in order to create a p channel CNT FET. Number 1, single crystal silicon substrates are cleaned and coated with around 120 nanometer of silicon dioxide, that is SiO2. Okay, then the second point, the single walled carbon nanotubes, that is SWNT, are produced by laser ablation or CVD. CVD means chemical vapor deposition. Okay, next point, the nanotubes are cleaned and untangled by sonication. So here sonication means it is a process where sound energy is being applied. Okay, so it is applied for untangling. That means in order to free the tangled or twisted state. Okay, so the nanotubes are free from tangled or twisted state by the process called sonication. Okay, next point, the nanotubes are diluted with 1,2-dichloroethane solution having a density which is adjusted to yield 1 nanotube per a given area. Then the solution is spun into the substrate, and the placement of the nanotubes are confined using atomic force microscopy or scanning electron microscopy. Right. Next point, the metal source and drain electrode are created by using e-beam lithography and lift off. Okay, then the samples are annealed at a temperature of 850 degree for 100 seconds of time, and the metal carbide is formed at the carbon nanotube, and the metal junctions and hence contact resistance will be reduced. Now a mixture of SiH4, it is called a compound, inorganic compound called silane, SiLane. It is actually colorless and toxic in nature. It is a gas. Okay, so a mixture of this silane with oxygen, that is O2, is deposited at 300 degrees Celsius to create gate oxide. Right. Next point, the source and drain contact holes are opened in the new oxide layer, and the annealing is done at a temperature of 600 degrees Celsius with nitrogen for 30 minutes to densify the oxide. Then the gate electrode is patterned using the e-beam lithography and lift off with 50 nanometer of gate metal. Then the gas which is forming annealing is done by reducing the trapped charges in the oxide interface. So the result is a p channel CNT FET, and the nanotubes become p types when they are exposed to air, because the oxygen in the air will cause the Fermi level at the contacts to shift closer to the valence band. Okay, so the result is that the holes are now able to tunnel through a small barrier, but the electrons in that case are not able to tunnel through at a very large barrier also. Okay, so only the holes will be able to tunnel. Okay, so the band structure at the contact for the p channel CNT FET is shown in the figure. You can see this is the Fermi energy level and this is the contact region. Okay, the lower one is the valence band and the upper one is the conduction band. You have already read this in the band theory of solids. Okay, so this is the gate voltage having negative value and this is the gate voltage having a positive value. Okay, now the transfer characteristic is also shown in the figure, where the drain current ID is taken along the y-axis and the gate to source voltage, that is VGS, is taken along the x-axis at a constant drain to source voltage, that is VDS, which is minus 0.6 volt. Okay, so this is the transfer characteristic of the p channel CNT FET, and you can see the graph is coming out to be in the shape like this. Okay, so here from this transfer characteristic, it is clear that there is a little bit conduction when the gate to source voltage, that is VGS, is positive, right, positive in this case. Okay, but however this conduction is very small in order to turn on another transistor. So if the gate to source voltage is negative, then the transistor, means in this case where it is negative, then the transistor is turned on and will cause the increase in the drain current, okay, as it is increasing, okay, as it is increasing for the negative value of the VGS, right. Now this is about the p channel CNT FET. The next one is the n channel CNT FET. So from the name it suggests that it will conduct the electrons, okay, like that of in case of your transistor. In case of n type, we have the majority charge carriers as the electron. So in the n channel CNT FET, this will conduct the electrons when a positive voltage is applied on the gate, and it does not conduct the holes even at high negative gate voltage, means just the reverse of the p channel CNT FET, okay. And it can be created by two ways. One is the process called annealing and the other is called doping. So first process, let us see annealing. It is done to drive out the oxygen that was absorbed while the nanotube was exposed to air. Okay, so for this, following points are used or adopted. First, the single crystal silicon substrate are cleaned and coated with a layer of 120 nanometer, which is SiO2, that is silicon dioxide. Okay, then the single walled carbon nanotubes, that is SWNT, are produced by again laser ablation or chemical vapor deposition. Okay, then the nanotubes are cleaned and untangled by sonication process similar to the p channel type. Okay, then the nanotubes are diluted with again 1,2 dichloroethane solution with density adjusted to yield 1 nanometer per a given area. Okay, solution is then spun into the substrate. Placement of nanotubes is confined using atomic force microscopy or scanning electron microscopy. Then again the metal source and drain electrode are created by using e-beam lithography and lift up. Then the samples are annealed, okay, by a temperature of 850 degree for 100 seconds, and metal carbide is formed at the carbon nanotube and metal junctions, and hence contact resistance is reduced. Now this annealing is done at a temperature of 450 degree Celsius in nitrogen in order to remove the absorbed oxygen, and the mixture of SiH4, that is silane, and oxygen is deposited at a temperature of 300 degrees Celsius to create the gate oxide. Okay, so here the points are very much similar to the p-type CNT FET or p channel CNT FET. Okay, next point, the source and drain contact holes are opened in the new oxide layer. Now the annealing is done at 600 degrees Celsius in nitrogen for 30 minutes to densify the oxide. Now the gate electrode is patterned using e-beam lithography and lift up with 50 nanometer of gate metal. Okay, next point, the gas which is forming annealing is done to reduce trapped charges in oxide interface. Okay, so here the Fermi level, that is the Fermi energy level, is it is actually shifted up towards the conduction band, and the barrier for the electrons is reduced by removing the oxygen, and this will allow the electrons to tunnel through the reduced barrier. At the same time, the barrier for the holes is increased, and hence the holes will not be able to tunnel through the increased barrier. Okay, this is a spelling mistake, it should be same. Okay, so the result is will be your n channel CNT FET, and the nanotube will become n type, right. So the band structure at the contact for the n channel CNT FET is shown in the figure. Okay, so let us go to the figure, this one, the left side, which is the band structure at the contact of n channel CNT FET. Okay, this is the Fermi energy level, this is the valence band at the bottom, at the top we have the conduction band. Okay, so when the gate to source voltage is negative, then you can see the drain current will flow, and this drain current will increase rapidly when the gate to source voltage will become positive, right? Now this was the first process, which is called annealing. Now the come to the second process, which is called doping. Okay, so doping occurs with an electron donor such as like your potassium. So for this, following procedure is adopted to create an n-channel CNT FET by the process which is called doping. So first, the single crystal silicon substrate are cleaned and coated with 120 nanometer of SiO2. Okay, again very much similar to the process as we saw in case of your p channel, then in case of your annealing. Then second point, the single walled carbon nanotube, that is SWNT, are produced by laser ablation or chemical vapor deposition. Then the nanotubes are cleaned and untangled by sonication process. Then these are diluted with 1,2-dichloroethane solution having density adjusted to yield 1 nanotube per a given area. Then the solution is spun into the substrate. Then the placement of nanotubes are confined by using the atomic force microscopy or scanning electron microscopy technique, right? Then the metal source and drain electrode are created by using e-beam lithography and lift-off. Okay, now the samples are annealed with a temperature of 850 degree for 100 seconds, and metal carbide is formed at the carbon nanotube and metal junction, and hence the contact resistance is reduced. Then next point, the nanotube is doped with an electron donor. Okay, this is the case of your doping, electron donor such as potassium. Okay, now the mixture of SiH4 means silane and oxygen is deposited at 300 degrees Celsius to create gate oxide. Then the source and drain contact holes are opened in the new oxide layer, and annealing process is done at 600 degrees Celsius with nitrogen for 30 minutes in order to densify the oxide. Okay, next the gate electrode is patterned using e-beam lithography and lift up with 50 nanometer of gate metal. Now the gas which is forming the annealing is done to reduce the trapped charges in the oxide interface, right? So here the doping actually causes the Coulomb blockade to shift downwards, and the Fermi level is pinned down by the doping and does not move. Okay, so here this is the same band structure of n-channel CNT FET which is created now by doping. Okay, now the transfer characteristic of this n-channel CNT FET having the drain to source voltage equal to 0.5 volt is shown in this figure, this one. Okay, so you can see the drain current in ampere is taken along the y-axis, and here the gate to source voltage is taken along the x-axis. So this is the curve. Okay, the curve is coming out to be like this. So here from the curve or from the transfer characteristics, it is clear that the small drain current will decrease to zero value when VGS is equal to minus 0.5 volt, and beyond that it will again increase with the increase of VGS on either side. Okay, now one more important thing, as you have seen in the band structure, this is the contact region of the source and drain, and this is called Schottky barrier. Okay, SCHO TTKY, Schottky barrier, and it is responsible for the on current of the device. Okay, now I have taken this CNT based transistor from another book also, where many other things are also given in details. And you can see, besides that, very importantly, it has given the working of the single walled carbon nanotube field effect transistor, that is SWNT FET. Okay, so you can read it. Besides that, again, it has given about the advantages of CNT FET. This is very important. Okay, various points are given like better control over formation of channel in the device, then high electron mobility and hence better conduction, then lower threshold voltage, high current density, high transconduction, then high linearity. Besides that, it has some drawbacks. Okay, like that of your performance depends on the ambient temperature. Then the CNT FET is not much more reliable because its reliability is affected due to the avalanche breakdown in the semiconductor carbon nanotubes and due to the joule breakdown in the metallic carbon nanotubes. And multi-channeled CNT FETs are better than the single channeled CNT FETs. Then next point, the CNT FETs are having shorter lifetime as carbon nanotubes degrade in a few days when exposed to oxygen, and mass production in case of your CNT FET will poses difficulties because their production cost is very high. Okay, and also it has given about the comparison between the CNT FET with the conventional field effect transistor. Okay, the similarities are like single wall CNT behaves as the channel for the charge carriers, then gate voltage controls whether the channel conducts or not, then function of source and drain is similar to that of your conventional FET, but it has also some dissimilarities like your source to drain contacts are formed from the metal contacts rather using N plus and P plus, which are heavily doped semiconductors. Then no doping required for creating N type or P type FET. Then the type of CNT FET depends on number one, working function of the metal which is used as the source to drain contact, and number two, the band gap of the CNT. Okay, then finally the application of CNT based transistor. Okay, this is also very important. So it may be used in new generation of displays for cell phones, TVs and computer screens. Thereafter, its next application is, there are particularly promising for wireless communication technology which requires a very high current flowing across a relatively smaller area. Then the CNT based transistor switching are at least 5 times faster than the silicon based transistor, so they do so with much less power than their silicon based counterparts. Okay, this is a very good application and plus point about the CNT FETs. Then lastly, the nanotubes ultra small dimensions will make it possible to rapidly change a current signal traveling across it, which could lead to substantial gains in the bandwidth of the wireless communications devices. Okay, so at the end, I advise you to go through the PDF completely, and as I said, I have combined the CNT based transistor taken from two books. Okay, so you read it mindfully and take the valuable useful points that are given in both the books and make your note accordingly. Okay,
Thank you.